Hi everyone, welcome to another practice problem walkthrough video from physacademy.com. In short, in this video, we'll cover a problem that combines the conservation of energy law and kinematics equations with an oscillating motion. Let's read and then work through this problem together. An object with a mass of 9 kilograms is in equilibrium while connected to a horizontal spring of a constant of 100 newtons per meter. The other side of the spring is fastened to a wall, and we can neglect the mass of the spring. A second object with a mass of 7 kilograms is slowly pushed up against M1, compressing the spring for 0.2 meters. The system is then released, and both objects move to the right on a frictionless surface. When M1 reaches the equilibrium point, M2 loses contact with M1 and moves to the right with a speed of v. In Part A, determine the value of v. In Part B, how far apart are the objects when the spring is fully stretched for the first time? Let's start with sketching 3 stages of the system. The first stage is when the spring is compressed for 20 centimeters, and both objects are ready to be pulled by the spring. At this stage, both objects' velocity is 0, so no kinetic energy is involved, but the spring is compressed and storing a bunch of energy ready to fire. Then in the second stage, both objects, together, pass the equilibrium point. At this point, the spring is at rest, meaning it is not compressed or stretched. Meanwhile, the kinetic energy is maximum, therefore, the object's speed is as high as it can get. A moment after this stage, M1 will stretch the spring, therefore, its speed will drop, but M2 will continue its journey with a constant speed as nothing is pushing or stopping it. Then, in stage 3, when the spring is all the way stretched, so M1 stops moving for a moment, and all of its kinetic energy is converted to the spring's potential energy. In the meantime, M2 is still continuing its journey at a constant speed. Part A is more about the connection between the first and second stages. Part B focuses more on the connection between the second and third stages. Now let's focus on Part A. In this part, we are asked to find the speed of M2 as it passes through the equilibrium point. We know that both M1 and 2 have the same speed at this point, so we can treat them from the initial position to the equilibrium point as one object with a mass of 9 plus 7. Alright, we start by listing our knowns and unknowns of Part A. L0 is how much the spring is compressed at stage 0. L for the length and 0 for the stage number 0. L0 is equal to 20 centimeters. M1 is 9 kilograms. M2 is 7 kilograms. Ks is the spring stiffness constant, which equals 100 newtons per meter. And Vm11 and Vm21 are equal, and we are trying to calculate them. V for velocity, M2 for mass 2, and 1 for stage number 1. First, I'm going to write the conservation of energy equation between stages 0 and 1. On stage 0, both objects' speed is 0, so they have no kinetic energy. But the spring is compressed and holds a lot of energy. Let's call it U, S, for the spring potential energy and then subscript 0 for stage 0. Then, at stage 1, the spring is not compressed nor stretched, so it doesn't have any potential energy anymore. But all of its energy is converted to the kinetic energy of M1 and 2. Let's call it KE1. Next we are going to write down the equations for the spring potential energy and the kinetic energy. We can mark out 1/2 on both sides. Let's mark the known and unknown variables. Alright, this is good, because next we can rearrange this equation and solve it for Vm21 or speed of mass 2 at stage 1. After rearranging the original equations, we get to this equation. Before plugging the numbers in, I'm going to take a few seconds to check the units to double check my work. Trust me, checking the units totally worth it. The spring constant is in newtons per meter, L is in meters, and the mass is in kilograms. Remember, Newton is the short way of saying kilograms times meter divided by seconds squared. Then, we can cancel out more units, and at the end, we get meters per second, which is the standard unit of speed. Let's go back to our original calculation and plug in the numbers to find the final numerical value of the speed. After plugging in the provided numbers, we get half a meter per second for the speed of mass 2, but remember, at stage 1, both mass 1 and 2 have the same speed. For part B, we are asked to find the distance between m1 and m2 when the spring is fully stretched, therefore, m1 is stopped for a moment. Before diving into the calculation process, let me tell you how I analyze the given cues. When we have two objects moving on the same time scale, we need a coordinate system to define their positions separately to find the distance between them. The other thing is that time is the key variable that connects the equations of motion of these two objects together. So there will surely be time calculations along the process of answering this question. Now that we know we need a coordinate system, as a rule of thumb, the best origin for the coordinate system is the equilibrium point of the oscillator. So let's sketch our coordinate system and then analyze the time it takes for mass 1 to go from the equilibrium point or stage 1 to stage 2, where the spring is fully stretched. After mass 1 passes the equilibrium point for the first time, one period of its oscillation will be like this. This equation gives us the time it takes to go through one period of oscillation. But here, rather than the whole period, since going from x equals 0 to x equals L2 is the quarter of a complete period, we can divide this number by 4. M1 and Ks both are given, so if in the rest of the calculation, we need to know the time it takes to go from stage 1 to 2, now we have it. Next, let's see how we can calculate L2, or the position of mass 1 at the final moment from the origin of the coordinate system when the spring is fully stretched. My first guess is using the conservation of energy. Conservation of energy equation for mass 1 between stages 1 and 2 has only two terms. On the left-hand side, we have Ke of mass 1 at stage 1, right as it passes through the equilibrium point. On the right-hand side, we have a spring potential energy for when the spring is fully stretched and mass 1 for a moment stops. We get the following equation using the kinetic energy and spring potential energy equation. After crossing off 1/2 from both sides, we can check the knowns and unknowns of the equation. As you see, other than the L of mass 1 at stage 2 that we are looking for, every other variable is given. After rearranging this equation, we get the following equation. Again, before plugging the numbers in, I'm going to check the units really quickly. Mass is in kilograms, Ks is in newtons per meter, and velocity is in meters per second. After canceling out a few units, we get meters, which is good news for us as I was expecting the unit of LM12 to be in meters. After plugging in the given values for mass 1, the spring stiffness constant, and the velocity of mass 1 at stage 1 right as it passes the equilibrium point, we get 0.15 meters or 15 centimeters. Now that we have the final position of mass 1 with respect to the origin of the coordinate system, we can check mass 2. For mass 2, I'm not going to use the conservation of energy because its speed from stage 1 to 2 is constant and doesn't change. So our only option is to use kinematics. The equation of motion for an object that moves with a constant speed is the following equation. From part A, we know v or velocity is 0.5 meters per second, and earlier, right at the beginning of part B, we calculated delta t, which was a quarter of a period. Replacing delta t with the equation from the period calculation, we get the following expression. Then we plug in the numbers and get about 0.236 meters for the final position of mass 2. The last step is to find the distance between the final positions of mass 1 and 2. After plugging in the number we found earlier, we get 8.6 centimeters. But what if we were asked to sketch the position versus time of these processes? First, let's mark down the initial position where mass 1 and 2 are both on the left-hand side, and the spring is compressed and ready to fire. Then we mark the equilibrium point, which happens to be at the origin of the coordinate system for us. Next we mark the final positions for mass 1 and 2. From the initial point to the origin of the coordinate system, we know the curve is a quarter of a sine in blue. After both objects pass the equilibrium point, mass 1 continues as a sine function, but mass 2 is free and goes through a constant speed journey. Thank you very much for watching this video. Please check our website, physacademy.com, or our YouTube channel for more practice problems. If you found it helpful, by subscribing to our channel, you can provide the best support for our work.